We're super excited today to have Colette Alexander, who is bringing to us a topic that's near and dear to my heart and to many others. In fact, just before everyone joined, Colette and I were talking about one of the challenges that DORA faces. And one of those challenges is that there are a lot of DORAs out in the world. There's, DORA that we all know and love and care about. There's the Digital Operational Resilience Act. There's the Explorer that maybe you or your children or nieces, nephews, youngsters in your life really love. There's also, as we were talking about, the in some states in the US, designated outdoor refreshment areas. So which DORA are we talking about when we talk about DORA? Well, we have a challenge in our industry where when you say a word, everyone hears that word slightly differently. And it's not because we're pronouncing it differently or our ears work differently. It's just that we internalize the definition of that word very differently. Resilience is definitely one of those words in resilience engineering. And so I think having Colette come along and speak to us a little bit about that is going to be super awesome. Those of you who don't know Colette, I've gotten to know her over the past year or so. She does a bunch of amazing things. There's she and another co-host run a podcast called This Is Fine. It's a podcast all about resiliency. She has a master's degree from Lund University in human factors and safety systems safety. She is also the president of the Resilience in Software Foundation. So without any real further ado, Colette, thank you so much for joining us today. We're excited to have you come speak with us about resilience. Oh, sorry, I do have a little bit of further ado before I hand things over to you. But while I'm wrapping this up, if you want to start sharing your slides, that will help. Sure. So typically, we do a short presentation, then we have time for a lean coffee in these meetings. But we've been mixing up the format here a little bit. Colette's going to have a slightly longer presentation today, in which we will have some time for Q&A and discussion following that, but we won't use the lean coffee format. But Colette has agreed to come back sometime in the future, in the next few weeks or months. We'll get that scheduled and we'll run a lean coffee discussion specifically around resilience engineering. All right, that's all the ado I have time for today. Colette, thank you again for being here. Right over to you.
Thank you, Nathan. Yeah, I'm super excited to also have this be a conversation, and I hope there's plenty of time for questions. We'll arrange lean coffee, but hi, everybody. I'm Colette. Let me just go into slideshow mode. Cool. So I've titled this presentation, Resilience Engineering, a Primer for Curious Software Engineers. And my hope is that we're going to talk about resilience engineering, talk about what it is, maybe talk about what it isn't. But first, some background on me. Hi, this is me. Nathan already mentioned who I am, but I work in tech. I'm the president of the Resilience in Software Foundation, and I play the cello for rock bands. Fun fact. That was my career when I was in my 20s, and I moved into software in my 30s, and now I'm in my 40s, and so I get to do both, I think is the answer. Those are some places that I've worked, and that's the Lund University symbol, and then down at the bottom there is the Resilience in Software Foundation logo. You can find us at resilienceandsoftware.org. What we're going to talk about today. So I figured you all can interrupt me. I can see the chat on the side of the screen. So if you don't want to talk about this stuff, let me know and I'll try to adjust on the fly. But I figured we would talk about what resilience engineering is, why we should care about it, and what we should do about it, and then have some moments for Q&A or what the fucks or whatever at the end. Cool. So yeah, this is me. I'm going to go back to me for a second because I have to tell a little bit of a story about how I got into reliability. And that's really because I love mess. I love being around when things are breaking. I love being around when everything is sort of hitting the fan. I find that the most interesting and awesome moment to be a part of a team, to be trying to improve things at a company. And so that's what initially drew me to reliability. I was working at Spotify, and I was part of the business that was having some issues with reliability. And so I was asked to sort of lead a working group to help fix it. And I started by tackling it like getting all my mean time twos, getting all of the stats that I possibly could, and sort of putting my head together with a bunch of engineers and trying to figure out what the statistics could tell us. And I found myself getting really frustrated. I still couldn't look at these numbers and make sense of them and what they should be telling me and what we should be doing next because of them. While all of that was happening, I was also doing research on the side. So I was kind of looking at talks. I came across a guy named John Allspaw. Some of you may have heard of him. He invented DevOps, or was one of the people who invented DevOps, I guess, at the time that it happened. And he was talking about learning from incidents and resilience engineering. And so I was like, all right, well, I got to learn about this stuff. And I ended up learning how to do in-depth incident analysis from John and Dr. Richard Cook. And then I decided to go to Lund and get my degree. And that's when I realized that, holy crap, safety is a science. I have my master's degree in human factors and system safety. But this was like a real revelation to me, right? I had been working in tech and reliability adjacent spaces for a while, but I did not understand until that point that safety was a science. And resilience engineering is grounded in this safety science. So I'm going to try my best to take you on a speed run of like some greatest hits from the safety science that came before resilience engineering, which I hope helps you all understand what resilience engineering means. All right, here we go. I'm going to do my best. All right, first up, there's this guy named Heinrich. He is basically a person who works at an insurance company, and he has his job is to basically say, okay, like, why are bad things happening at all these companies? This is back in the 30s, right? So it's 1931. He comes up with this domino theory for industrial accidents. And he says that, you know, there's all these different influences in an accident, and that when one domino falls, the others fall and lead to eventually an injury, right? Because at the time that was the bigger risk. And so he initially comes up with this idea of this linear chain of events. It might start at one point, but then it eventually leads towards injury. And some things can help right the dominoes, but mostly you're just like, this is how we look at an event that happens that causes an injury. All right, so this might actually look kind of familiar, and I like to put this right after Heinrich's dominoes because this is much later in time. This is in 1990. Jim Reason comes up with something called the Swiss cheese model. Now, you all might have actually seen this recently. This graphic made the rounds during COVID because when people were talking about how viruses can sort of, or epidemics happen, it's because of a lot of different things. A lot of different things have to go wrong, or a lot of different protections against the virus have to fail in order for the virus to get through and to infect a human. That would be like infection agents that happening, your mask falling off, or somebody else's mask falling off, you get it. So these are very similar in that they take a linear view, again, of the accident happens at the end of the chain, the hazards occur along a linear chain, and you know, there might be some types of protections against these accidents that are controls or processes. So that's, but if you notice, it looks a lot like the dominoes, right? So we're still kind of in this like linear view of how accidents happen. Then I'm going to take you, so there's this linear view of how things happen. Some people are thinking about safety industrially, and then 3 Mile Island happens. Going back in time again from 1990, Jim Reason. The origins of a lot of what we consider modern safety science come from 3 Mile Island. For those of you who don't know, 3 Mile Island was a partial nuclear meltdown. It happened in the 70s. And one really important thing is that out of 3 Mile Island came kind of 2 different reactions. One was the operators really messed this up they really like caused all of these problems and caused this partial nuclear meltdown. But another perspective was, oh my gosh, the control centers in nuclear power plants are like not really well set up to actually tell operators what's really happening, because ostensibly, you know, the crux of 3 Mile Island was that operators' actions made it worse, made a partial meltdown more likely, based on the fact that they didn't actually understand precisely what was happening. 3 Mile Island leads directly, for people who are noticing the latter thing, the fact that controls weren't sufficient to help operators understand what was actually happening in the nuclear power plant. 3 Mile Island leads directly to something called cognitive systems engineering. This is a book called Joint Cognitive Systems. It's written by David D. Woods and Eric Hollnagel. And this is the first time that people have been approaching a problem between machinery and humans, human operators and machinery, as a single system. That's the proposal of cognitive systems engineering, that these things, rather than be considered separate, are actually, we should look at machines and humans together and how they interact, and look at them as a single system to achieve an outcome. Before that, you would have looked at things like machines automating away some human tasks, but doing it totally separate from the human. The idea was that they should be totally separate things. Looking forward in joint cognitive systems, this cognitive systems engineering discipline, you finally see those things coming together as a single system, people looking at the holistic system and thinking about achieving outcomes together rather than separately. This is a really important predecessor to resilience engineering because it considers the socio-technical system, I guess, as a whole. You might hear folks who are interested in resilience engineering refer a lot to socio-technical systems. So this is where the socio-technical system is a unit of study and a way of thinking about problems. Also, Dave Woods kind of founds resilience engineering with some other scientists. So it's and Eric both do. So they come to this first, and then resilience comes out a little later. Another important thing that comes out of 3 Mile Island is what I would call a sociological lens. So Dave and Eric tackle the more scientific lens, but there's also a sociological lens that comes out of 3 Mile Island that talks about, Charles Perrow wrote a book called Normal Accidents, and it talks about particular technologies that are high risk, and that ostensibly introduces us to this idea of coupling and complexity. And the most famous thing you'll see out of Charles Perrow's book is this figure here, which talks about coupling and complexity on different, on a XY scale, and really focuses on these highly complex, tightly coupled technologies: nuclear power plants, nuclear weapons, space missions, military early warning systems, chemical plants, aircraft, DNA. To kind of be very specific, when Perrow talks about complexity, he talks about a characteristic where components can interact in varied and potentially unanticipated ways. The opposite of complexity in Perrow's definition is something that's very linear. You can see that on the diagram towards the left. And so dams, for example, are very linear in their structure, but are also tightly coupled. Coupling for Perrow refers to how components relate to one another to accomplish a goal. So tight coupling would be that there are required sequences that are needed in order to meet a goal, where loose coupling would be that things are substitutable, parts are substitutable, or parts of the processes are substitutable. So for Perrow, the riskiest technologies are systems that have both tightly coupled and highly complex interactions. Perrow wrote Normal Accidents in 1984. So this was before kind of the internet starts to hit its heyday, right? I would argue that we work as technologists, we work with complex and coupled technology every day. Some people would argue, and have argued, that it's not as dangerous as a nuclear power plant. I think that there's a lot of room for debate there. And I think that we have examples of the last 10 years of things that technology has impacted or ways that technology has gone awry. I mean, internet technology, that would sort of lead us to believe actually that can be quite dangerous. So this is my argument, that we work with complex and coupled technology every day. And so safety science applies to us as much as it applies to these other sort of genres. Now, I have two exhibits for you in that argument. The first is a screenshot of Slack from a couple gigs ago, where my friend Scott wrote me and was like, I thought I would try to visualize all the service dependencies as outlined in service metadata. That was a mistake. And I just put a smiley face on it. So I think this illustrates complexity really well, unlike the sort of front of world where microservices rule, right? And also my favorite XKCD comic, it made an appearance in my thesis at Lund. All modern digital infrastructure, and then the random open source projects someone has been thanklessly maintaining since 2003. Which, whenever a technologist that I know sees something like this, they laugh I hope you're all laughing, in recognition, right? You recognize that this is a true representation of how the internet works. And it is both terrifying, but it's also funny. And sometimes when there's not much we can do about something, it also helps to laugh. I think also that this comic emphasizes something that in us and evokes, at least in me, perhaps in you, a saying that Dr. Richard Cook had at a really wonderful talk at a Velocity conference a few years back. And that is, you're not surprised your systems are down. You're surprised that they were ever up at all. And this is a fundamental perspective shift, right? That we have. So this brings me to my next sort of caveat of what resilience engineering is, which is it examines what keeps our systems going every day. So rather than looking at that previous, couple of the Swiss cheese and the dominoes, which is like, what led to this accident? What is the linear chain of events that led to this accident? It desires to look at what actually keeps our systems going every day. It acknowledges the reality that our systems operate in a constant state of degradation, right? Dr. Richard Cook wrote a wonderful treatise on this called How Complex Systems Fail. If you just type how.complexsystems.fail into your web browser, you will see a long list it's not that long. I don't know, it's like 12 points or something, but they are fundamental realities of complex systems, regardless of whether you're talking about the medical world, the nuclear power plant world, or the software internet world. I highly recommend reading it, but it really gets at these issues of, we're surprised that things are up at all. There are a ton of things that are keeping things running every day, and degraded operations, are the norm, and failure are the norm in complex systems, right? They aren't the exception. And so we move instead from asking ourselves, what is the root cause of how this perfect system broke, right? This is an old way of thinking. This is pre-resilience engineering, to what contributing factors were at play in making the system move into this failure mode, right? So rather than, the system's constantly in a state of degradation. So we just happen to tip, if we're having an incident, we happen to tip it into a failure mode that may be unacceptable to our internal devs or to our external users, right? Whatever that our definition is of incident, we've just tipped it into there. But that, just because, we want to pull it back again, doesn't mean we're going back to some perfect system, right? And looking at it as a perfect system doesn't do us any favors. I would argue too that we actually, with resilience engineering, rather than just contributing factors to this tipping point into failure, what are our normal ways of working that allow us to keep our systems running? Because probably everybody showed up at work today not wanting to cause an incident, doing things the way that they normally have for weeks and months on end, right? And so if we examine the normal ways that we work, that we keep our systems running, then we can also see the patterns that lead to its failure. They're the same thing, right? I have a big thanks to John Allspaw. I think he would also add, and maybe Dave Woods would add, what adaptations are happening around us to keep our systems running. So adaptation is a really important word. The things that operators go through constantly in order to continue to keep things running, looking at the holistic system as constantly adapting, constantly adjusting, constantly maintaining. That is sort of at the center of what we consider resilience engineering. Okay, so we've arrived here. I've taken you on a little bit of a speed run, I admit. And now I just want to reiterate this. I didn't say it up front. I wanted to say it after the history. And that's these are what we call the 3 R's in the resilience engineering world, right? They are distinct things. Robustness is the ability of a system to perform under a wide range of conditions. Robustness can be planned for. So an example of robustness that I often use is, hey, holidays coming up. We're a consumer-facing company. We might want to look at our auto-scaling capabilities and make sure that we're prepared for a certain level of traffic, right? We can think through these things, we can rationalize about them, we can see them coming around the corner, we can say, hey, these are things we can plan for. Resilience is the adaptive capacity within a system to recover from unanticipated, unexpected events. Resilience is key to resilience is that it's the big stuff that you can't plan for, right? It's the thing that you cannot possibly foresee, which it turns out is a lot of things, especially in a complex world of tech, right? Reliability is the measure of how consistently a system has performed in the past. So reliability looks backward, and given a set of measurements or a set of constraints that we have around those measurements, we can tell how a system has performed. The adaptive capacity in resilience is always in people. Like technical systems are not, purely technical systems are not typically very, they're brittle. So that's really important. The other important thing that Dave Woods likes to talk about a lot is that resilience is a verb. So resilience is constantly in motion. It's not some kind of thing that you it's not like a binary, you either are or you're not. And every system has resilience in it. If it's up, if it's capable of accomplishing its goal, it has resilience. So I hope these definitions make a little more sense given the background. I see somebody talking about J. Paul Reed and his thesis, so I'm really glad we're talking about Lund theses. That's super great. So we've got a definition of resilience, and now I think, and this is a question I always ask myself still to this day, what the heck is resilience engineering? How do you engineer resilience? The best way that I can sort of talk about it is I'm cribbing here from Dr. Richard Cook's talk on bone. So you can Google Dr. Richard Cook bone talk. He talks about the resilience of bone. And to sort of summarize that, there are 2 different ways to engineer resilience. One is taking advantage of existing resilience within your systems. So you can examine what's going on currently in your socio-technical system and identify the resilience in it and either enhance it or thank it or make sure that you support it in any way possible. In the case of bone, this is setting a bone. right? Bone has inherent resilience in it in that it will self-heal. And so the analogy that Dr. Cook draws is around, setting bone. What's interesting too about setting bone is that we can take advantage, like setting bone has been going on for millennia, and it was taken advantage of. The systems of resilience within the bone were taken advantage of before they were even really understood. So you don't even need to fully grok them in order to take advantage of what's there. The second way requires more grokking, more understanding, which is altering aspects of the system to increase its resilience. And so the analogy to draw here with the bone is, with bone, especially if you're in menopause as a woman, your bone might start to go through a transformation called osteoporosis, where it loses density and it loses the ability to kind of heal as well. Doctors can give you estrogen or hormone replacement therapy that allows you to avoid having that happen or head it off the path. That's chemically altering your system in order to increase its resilience, the bone's resilience. So that's also an option. It's just harder to do because you have to understand more. And exactly, resistance training, right? And yes, we're talking about the socio-technical system. Remember, resilience of any system lies in the socio part of the socio-technical system. The technical system itself can't ever be resilient on its own. All right, so clear as mud, right? We've got there. We understand what resilience is, and we understand how one might take advantage of doing some resilience engineering. Makes total sense, right? Yeah. All right, we'll get to the rest of the questions because I need to cover the next part of this talk, which is why should you care? And I have kind of 2 points for you here. They're going to be a little on the quick side because I think actually I'm more curious about why you think you should care, but I have 2 suggestions for you of why you should care. One is that if people don't see their systems as they are, they can't ever really improve them, right? And that resilience engineering seeks to understand how the system actually works as it is. In the resilience engineering community, sometimes we're known to take pot shots at action items. This is where I find the opportunity to do that. So a lot of times what we find when folks are doing action items after an incident, say they're in a postmortem and they're like, we've gotten to the last 10 minutes of the meeting. It's time to do those action items. And then they shoot off a bunch, right? And, who do you think is going to do better? Actually, John mentioned this yesterday when I was talking to him in a webinar. He said, who do you think is going to do a better job coming up with relevant action to take after an incident? People who have spent 20 to 30 hours understanding what actually happened during the incident with the systems involved, or people who just hung out for 45 minutes and argued about a timeline and maybe some people understand some of what happened, but nobody's actually taken the time to really dig in, right? And I think that this is true, right? Your action items from your incidents are going to be a lot more relevant the more and the better you understand the system. And I think that this point hits at that, right? My next case is a part of our AI panic. So a lot of people are wrong, or I posit this, right? A lot of people are wrong right now about AI and what it's going to do for the world and for you all as engineers. And it's going to cause a lot of systems to go down in the future. And that's why resilience matters, right? My number 1 question when somebody talks to me about AI right now is what happens when there's no human who knows how a part of the system works, but the humans still have to fix it when it's broken. And this is my favorite meme that I've created in a while, which is if you think your LLM generated code is anything other than job security as an SRE. There we are. Cool. So those are my 2 cases for maybe why you should care about it. I would love to hear from you about why you think you should care about it. What should we do about it? okay, so there's this resilience engineering thing. It exists. It's a science. It's grounded in a science. It's, you know, people all over in aviation and everything practice it. Cool story. So what do we do about it? Well, I like to say keep calm and learn from incidents. So learning from incidents, I think, is the #1 piece of value that anyone can get out of resilience engineering right now. In any organization that you're a part of, in any stage of maturity, in any sort of place that you're working, you can focus on learning more deeply from your incidents. You don't have to do all of them. You could do 1 a month. But I think that this is probably the #1 thing you can do. Because building shared models of how your systems work among your human operators, that's increasing resilience in your organization. Practicing in-depth incident analysis is the best way to do that. And I think it's interesting, right? Like resilience engineering at its core, as I mentioned, is about examining how people do work every day. It's not necessarily about focusing on what went wrong, right? That's a little bit antithetical. But the truth is that we're deeply human and we love a good incident story, right? It's a huge draw of attention for the organization naturally. And so taking advantage of that attention on the incident as an excuse to learn more about your systems and how they actually work rather than how everybody thinks that they work is a really valuable thing that you can do right now. Another thing that I would advocate for is treating any standard practice, that things that you just do because you just do them, cough 5 whys, or any other practice that you might have, examine those practices like you are scientists. Some of the value of treating our world through a scientific lens, which led to kind of our thinking around resilience engineering, right, is that we can interrogate practices that we previously, that are previously just the way that we do things. Well, why do we do them that way? Is it actually helping us? And I think that resilience engineering as a practice encourages us to do that, because it encourages us to look at how we're actually working through that lens of it being a science. There are laws, right, within resilience engineering. You can Google some of them: graceful extensibility, reciprocity, there are a ton of different things that in particular Dave Woods has worked to identify and examine and sort of write up as laws, like gravity as a law, right? And if you're curious, if you want to learn more, you can always join the Resilience Software Foundation. We have a Slack, we hang out, we talk, all that stuff. So that's it. I think I did okay on time, right?
Did great.
All right.
Yeah.
And then I do this. You can find me at Colette at resiliencesoftware.org, Colette on Rand Slack, or the YouthNIC Slack. I'm everywhere. I'm on all the Slacks. So just come find me if you want. I'm not on any of the. I'm also on LinkedIn, but only because I have to be. But I'm not really on any of the other socials these days for my mental health. All right. Cool. Thanks.